Action.
Good afternoon, everyone. We're PCG, Prime Consulting Group, and today we're excited to present to you the design phase of the State Road 836 Southwest Extension Project. First, let me introduce the members. I'm Emma Venturini, and I'm the project manager.
I'm Maria Mendoza, I'm a structural engineer.
I'm Raniel Arecibo, a structural engineer as well.
Hughes Shaw, geotechnical engineer.
Randy Castillo, environmental engineer.
Saul Kalman, drainage engineer.
Gilad Gawlowski, transportation engineer.
My name is Victor Asa, and I'm going to be taking care of safety.
First, let me give you a brief overview. I'm going to give an introduction, and then my partners will start talking about environmental analysis, geotechnical analysis, intersection design, bridge design, followed by safety, pavement design, drainage, aesthetics, and then I will come back to talk actually about the aesthetics, project schedule, and cost estimation. As some of the members weren't here for our the members of our audience weren't here for our PD&E study presentation, I wanted to make sure you know why there is a need for this project. Well, the Southwest Miami-Dade area has been increasing in its population and in employment, and that's why traffic has also increased. Therefore, our objective for this presentation is to come up through careful calculations with a design that is also reasonable in cost. Here is our prime alignment. It was a hybrid between alternative 1 and alternative 2 that MDX proposed. As you can see, it goes down parallel to 137, turns, and then also goes down parallel to Chrome Avenue. In order for us to show you a more realistic and vivid experience of our intersections, we went ahead and contacted an architect who helped us design a 3D modeling of what our intersection would be at 42nd Street. My partners will develop on that later.
Well, hello everyone, my name is Randy Castillo, and I'll be talking about the environmental analysis for this project. As we previously said on the PDME report, there is a lot of animal species that can be endangered with the construction of this project. It's our job to provide all the signalization and barriers that needs to be done in order to protect these animals. These are going to be provided by the constructor, and they will be put under the DOT standards. As we said on the PDME staff report, we are proposing the extraction of the gas station that is located on 8th Street and Chrome Avenue. The reason why is because this gas station have 3 underground tanks of gas and oil, and also an underground tank of waste oil of 300 gallons. We opened 10 borings on the area. As you can see, the red ones are considered the one with more contamination to the soil, and all the way down, the green ones represent no contamination for that soil specifically. Why are we so interested on preserving this area? It is because the Bird Drive Recharge Basin is part of a comprehensive Everglade restoration plan. The purpose of this plan is to reduce the seepage from the Everglade National Park, and also to improve the groundwater flow and peak flow reduction. So we can see in this table, there will be a cost for that because we're going to need to excavate the soil that is contaminated due to the gas station, and also we're going to have to fill that area with good materials and do some landscaping and vegetation, free vegetation to the area. Well, I'm going to do a brief introduction on the geotechnical analysis now. In any project, the first thing is to do a field exploration. For that, we need to do certain tests. We did approximately 1,000 CPTs around the whole alignment, and 2,500 SPTs in total. Also, with the sample that we get from the site, we did some laboratory testing, like sieve analysis, moisture content, etc. Well, after taking all that information into account, we realized that we had 3 main layers, and also that we had from 0 to 3 feet of mud or organic materials. After 40 to 50 feet, we encounter really hard layers that my coworker here is gonna go into the foundation later. For the non-elevated section, this is the cross-section area of our design, and we are proposing the extraction of the first 4 feet in order to create a more stable road.
In order to classify the soil, we had to do a standard penetration test. And the boring's depth depended on if it was in an elevated section or non-elevated section. For the elevated sections, the boring depth went to a depth of 40 to 60 feet, while for the non-elevated section, they were approximately between 15 to 30 feet. And with the soil that we collected, we did a grain size distribution, and we collected the moisture content along with the density of that specific soil. And in the first 30 feet of our layers of the soil collected, we basically encountered 3 main materials. Between 0 and 10 feet, we had sand and lime rock fill. And for the last 27 to 30, we basically had limestone. Groundwater conditions. The water level in our area was estimated between 3.5 to 7 feet. And the factors that affect the water level are climatic changes, construction activity, rainfall variation, along with water runoff. And due to those factors, we had to take them into account in construction activities and how they'll impact our construction. And with the water collected, we also did the corrosivity test in order to determine their pH level and how they'll affect the foundation. Foundation design. The foundation that we used depended on if it was in the elevated section or non-elevated section. For the elevated section, we use deep foundation, and the reason is in order to support the high loads of the superstructure, we had to use deep foundation, and also of the poor quality of the soil that we found in this area, which is mainly sandy and silty layers. And as you can see in this pic, those are a pile, and this is the pile cap, and this is the column that the pile are supporting. And driven pile. We use 18-inch squared pre-stressed concrete piles, and the reason we use piles is because they're high capacity to carry the high loads that we have, and they can be inspected before driven in the soil, and also they're non-corrosive, which that means they won't be chemically impacted by the water. And those piles, they were driven to a depth of 60 feet to reach the limestone layer. And for each column, we had an estimated of 4 piles. And each of those piles have a capacity of 300 tons. Mechanically standardized earth walls. The reason we use MSE walls is because they're easy to install. They don't require additional work after being installed. And also, they can handle large deformation. And and those MSE walls, they're basically located before every bridge or ramp that we had or alignment. And they had a height of approximately 18 feet. Their width were about 93 feet, and they were 900 feet long. And we had a total of about 20 MSE walls throughout our alignment. And inside those MSE walls, they had what you call asphalt fill, reinforced fill, and which is basically sandy and silty soil.
Hello, everyone. My name is Ariel Mendoza, and because of time constraints, my partner right now and I are going to tell you a little bit about the details of the design intersections and a little bit about the calculations that we do here. The first intersection that we're going to have is going to be on the southwest 145 Avenue. This in particular intersection is not going to have any entry or exit points due to the fact that that area is undeveloped right now. But we make it a bridge wide enough so in the future we can contribute, and if the area needs it, you can just attach the ramps. A vertical clearance and type of flooded beam, F5B. Flooded beams are more preferable by the EOT, that's why we decided to use them. With the type of beam we bury it through the alignment just because of the span of the bridges. The next intersection is gonna be at Southwest 147 Avenue. This one is a little bit more complicated. We're gonna have 4 ramps, 2 exiting and 2 entering in either east and west direction. Shortest we decided to go for 12 feet, because we're gonna use it as acceleration and deceleration ramps for the deceleration ramps. Again, the Florida beam with barrier in this case again is 100 feet bridge, so it's Florida beam 36. The next intersection would be at 8th Street. This is gonna be the more complicated intersection because we're gonna have a span of 300 feet. We're crossing over the canal and the traffic lanes. So vertical clearance should be about 16.5 feet. That's required from the LTOT PPM. And in this case, Florida beam 63 would be used because it's better for this kind of span. We're gonna have two bridges, simple part bridges at 150 feet each. And in the north part of the intersection, we're gonna have an entry ramp. And in the south part of the intersection, we're gonna have 2 ramps, 1 exiting and 1 entry. It's gonna be going from grade to the elevated section that we previously discussed that we were going to construct because of the cash basin that we wanted to maintain on the south part. This intersection is not gonna have any exit point for traffic going into west, because that would increase the price of the intersection significantly, because we will have to buy a lot more land from the Miccosukee, or we will have to do an overhead pass, which is, we have an intersection right less than 1 mile before, so vehicles that wanted to exit on this area should exit on the intersection before. Right after that intersection, we're gonna have the elevated section, which is approximately 2,300 feet, and it's gonna be elevated because of the reason on the pre-need report. The next intersection is at Southwest 42nd Street, and this is the 3D model that my partner Emily talked about, that we wanted to picture, you guys to picture how it would look like the intersection. And again, every time the ramps, in this case, we're gonna have 2 ramps at the south and 2 ramps on the north part. And every time the ramps need to cross a water canal, because the design speed for the ramp is only about 25 miles per hour, we can use concrete box cover per FDOT index 249. The next, all the other intersections will be kind of like following the same standards for our alignment. The only thing that varies is the span of the bridges and the type of beam that we're gonna use, and my partner is gonna elaborate on the calculations. The last intersection we have, again, as the first intersection, is just a simple span bridge, long enough so in the future, again, in this area, there's not much development, so in the future, if the MDX wanted, they can attach ramps, so you can just use, you have already a 6-10 bridge, I'm sorry. And now my partner is going to elaborate on the calculations.
Hello everyone. Again, my name is Ranel. I'm going to be talking about the bridge, the superstructure design of our bridge. First of all, I want you guys to have a better look at the typical section that we're going to have on all of our bridge, including the elevated section. For the barriers, we're using the 32F shape. For the deck, we're using reinforced concrete with a depth of 8 inches plus a 0.5 inch of sacrificial. The type of beam that we're using, the Florida beam, as Arian mentioned. For the bank caps and the columns, we're using reinforced concrete as well. So the most critical span that we're gonna have is gonna be about 150 feet, which is gonna be implemented at 80th Street, the interchange at 80th Street and at the elevated section. So in the following slides, I'm gonna show you the flexure and shear designs that we did for this type of beam. So after using an influence line and doing an analysis, we get that maximum moment for the live load, in this case of the truck load of HS 2044, is going to be around 20 cubic feet per lane. This is a picture illustrating better the position of that truck, which will generate the maximum moment that I just mentioned. The loads that were considered for these calculations, again, for the live load, the load of the truck, For superimposed dead loads, we use the weight of the side barriers and the bridge deck. For the dead load, we use the Florida I-beam 63, the weight of itself. And after calculating the moment that will generate due to those loads, we get a maximum moment of about 106 kips per inch. This is a moment diagram illustrating better the behavior of the moment to the whole span. So since these beams are pre-stressed, we want to calculate how much pre-stressing force we need to apply to this beam in the pre-stressing phase to work on that moment that I just mentioned in the service state. So after running through the calculations, we get that we will need 2602 kips of pre-stressing force. For the shear, the loads that we consider are pretty much the same. The only change will be in the lag load that we use 0.64 kips per feet of load lane, this is basically loading the whole lane of trucks. And as you can see, here's a shear diagram illustrating how the shear is going to look like through the whole beam. And as we expect, we're going to have the maximum shear at the support, which is 241 kips. And after calculations, we come up that we need to use number 3 stirrups at 4-inch center to center.
Okay, my name is Victor and I'm gonna be talking about safety. Safety for this team was a priority because following engineering ethics, whatever we do in our design needs to be safe. And I'm gonna talk about some of the factors and guidelines that we follow to make sure that our design was safe. Lighting is very important for safety, and for lighting we had 2 poles to choose from. We had the non-breakaway poles and the breakaway poles. Breakaway poles are preferable because when they do fall, they cause less damage to vehicles and the people driving. So that's why those are the ones that we chose for our project. Now, for using this type of poles, we need to understand their falling pattern. And we don't want the poles to fall and get into the other lanes and cause a bigger accident. So to avoid that, we follow the standards and we provide 2/5 of the mountain height to the back of the pole and 1 full mountain height to the side of the pole. For the median lighting, since we have 2 lanes in each direction, we're gonna have 250 watt luminaires, HPS, which stands for high pressure sodium, and a mountain height of 40 feet. The spacing, once we calculated it using the standard formula, we got about 208 feet separation for our luminaires. Now, for the horizontal alignment to be safe, this is some of the guidelines that we follow, which are very important for safe operations. Consistency should be sought, and sharp curves should not be followed by a series of tangents or flat curves, and sharp curves should be avoided in high areas, and reverse curves should provide a space for a smooth transition of the super elevation between the curves, and broken back curves should not be used at all because they are unexpected and they don't look good design-wise. Now, you can see here from the graph that for our design speed, that is 50 miles per hour, we're going to have a stop side distance of 495 feet. Now, for the vertical curves, we have two types of vertical curves. We have the crest and the sag vertical curves. Now, to calculate the minimum length that we're going to need